Elia Fioravanti, who will teach us about median spaces.
Great, thank you. Right, so median spaces, I will start with the definition straight away. And then there will be a lot of examples, and by the end of the examples, it should be clear why you should care about median spaces. So we'll postpone the motivation until then. Right, so, okay. So definition, a metric space is median if whenever you have 3 points, there is some unique fourth point that lies between any two of them, right? So is median if for any choice of x1, x2, x3 in X, there exists a unique other point M, which is going to depend on these three. Such that, well, the following holds. So it's just three equalities. You just want the equality in the triangle inequality when going from, from one of these points to another one, you go through this median. Right, so this, it's three equalities, so for every. So if the metric space is geodesic, right, all we're saying here is that there is one geodesic between any two of the points that goes through M. But I'm not assuming that the metric space is geodesic. It can be discrete, totally disconnected. In general, that can happen. But it is efficient to go M. Also, I'm just asking that there is some geodesic, but in general, there can be more, right? So I guess like some sketch of this would be bigger than this. Yeah. Oh, okay. That's going to be hard. Well, okay. I'll do better. And oh yeah, by the way, please scream at me. Like if you have a question, I might not realize. Right. So if you move along these things I've drawn, you should be thinking of a geodesic, but you might also have other geodesic. And of course, when you have this, well, you get a ternary operator. You get a map here that is important. So from triples into X is called the median, or the median operator. Okay, so let's see some examples. Okay, so what's the most obvious one? This is something that looks like a tree, kind of, right? So example number one is going to be trees. So, well, if you have a tree and you have some points in Z, there are, well, Z, they're going to span a unique tripod. And, well, the unique tripod is going to have a unique point of degree 3. That's precisely where the median is going to lie. So I've drawn a graph here, but the way I'm going to define trees is actually simply as 0 hyperbolic geodesic metric spaces, right? So any 2 points are connected by geodesic, and geodesic triangles are all degenerate. So graphs that are trees work, but it could be much more complicated metric space where the branching doesn't just occur at a discrete set of vertices, but just happens all over the place. So an R tree. And if you don't like this kind of space, you are probably at the wrong mini course, because somehow, like the reason and the motivation for median spaces that I'll get to in a moment really involves complicated, branchy, non-discrete spaces that arise as degenerations of nicer spaces. So the kind of spaces that one in practice has to deal with is definitely very like locally complicated. Okay. Example B is Rn. And since there are a lot of different mini courses this week for which Rn is going to be a special case, let me just write 3 metrics on Rn, right? So you have the L1 metric, right? Then you have the Euclidean metric, which is an L2 metric. And finally, you have the L infinity metric, right? So only one of these is median. The other ones are not. So let's see. So for instance, okay. So Rn with the L2 metric, with the Euclidean metric, is not median. Oh, am I writing small again? Is this readable? Kinda? Not really? Okay, this is a 2. Rn with the L2 metric is not median for n at least 2. And the reason is that this space is uniquely geodesic, right? So, if you have 3 points, there is a unique geodesic between any 2 of them. And if the triangle is non-degenerate, these 3 geodesics don't all share some other point. So you cannot have a point that does this, right? So if your space is uniquely geodesic, the only way in which you can be median is if you're actually a tree here, right? But so in general, a median space that is not a tree will need to be highly non-uniquely geodesic. So this is not median. So Rn with the L1 metric is median instead. So D1 is always median. And I guess the picture you can draw here is something like this. So if you have 3 points, you can always draw some L1 geodesics that look like this, that sort of like always move parallel to one of the axes. And moving along this thing, you are always geodesic, right? And you're going to have this triple point here that is going to be the median in this case. But of course, you have many other geodesics, right? So this would have also been a geodesic. This is also geodesic. And here, the median has a very nice characterization. So the ith, which makes it easy to check that this exists and is unique. So the ith coordinate is, you look at the ith coordinates of the 3 points, and you choose the middle one. So not the smallest, not the biggest, but the middle one. So the middle among xi, yi, z, I. Yeah, that's exactly what I'm doing, right? Yeah. So in each coordinate, you do the median on that coordinate. Yeah, that's right. And just a comment. So maybe we'll see this later in the week, but Rn with the L infinity metric is also not median, but somehow for the opposite problem that occurs here. So with the L infinity metric, this is not median now for n at least 3. And the point is that there is always a point m, but it's not unique. And here, the uniqueness part is also a very important part of the definition. So here, yeah, here, that's right. There is no m. Here, there exists m, but it's not unique. Okay, and sort of these 3 metrics both relate to 3 classes of spaces that are very important in geometric group theory. So median spaces are a generalization of Rn with the L1 metric. Cat-zero spaces are a generalization with Rn with the L2 metric. And injective spaces that we'll hear about this afternoon are a generalization of Rn with the L infinity metric. And more generally, this works for any measure space. So let me mention this because it's important for tomorrow. So more generally, L1 of any measure space is a median space for every omega mu measure space. And similarly, L2 is going to be a Hilbert space, so it's got 0, and L infinity is also going to be an injective space. And you recover Rn in the case where omega is just finite and mu is a bunch of atoms there. And there's a nice picture that you can draw here. Oh, maybe let me say, so this is a space of measurable L1 functions from omega into R, let's say, up to coinciding on a null set. So this here, the metric, the distance between 2 functions is just the integral over omega of the absolute value of the difference with respect to the measure. And here the median, you can actually visualize in a very nice way, provided that you can draw the functions. So let's pretend they're continuous. So let's say, e.g., in L1 of the interval, pretending that we're dealing with something I can draw, right? So this is the interval. So say that we have 3 functions. So this is F. Then there is some G. And I'm going to need another color. How about and H, right? Predictably, right? So the way you compute the median is you do this in every coordinate. Every coordinate are just like the points of the interval, and you look at the values. So the way you find the median is by always picking the middle strand between these three. So this. So this is going to be okay. So let's move on to something a bit more interesting. Example C are going to be Casio cube complexes that we've heard about this morning. And they are median actually in two different ways, related to each other, but different. So, so let X be a zero cube complex. So first of all, and this is the way that is like sort of like most useful for like geometric group theory. So you can just look at the zero skeleton, right? So the zero skeleton with, I think Nir called it the combinatorial metric this morning. Let me call it the hyperplane metric now for a second, right? So you take the zero skeleton and you have the distant function that is just, oh well, this is median. So let me remind you, this is just the induced path metric from the one skeleton restricted to the zero skeleton, but it's also the number of hyperplanes of the cube complex that separate the two vertices, right? And again, so the median is, it can be written in a very simple way. I guess maybe we'll see it tomorrow, but so there is always a vertex with that property, and the point is that you can look at every hyperplane on the cube complex. It has only two sides. So every point will lie on either one side of the hyperplane or the other one. And so for every hyperplane, there is going to be precisely one side that contains at least two of the 3 points. And for every hyperplane, you choose that side that contains the most points. All these sides you can show intersect, and their intersection is a single vertex. And that is going to be the median. So this is sort of the only vertex lying in all half spaces that contain at least two of the 3 points. Okay, so this is one way. But of course, cube complexes are not just the zero skeleton, right? They also have all the cubes, and you might just want to have them filled in because that's a setting where the Casio metric is defined, and you can do that. So another thing you can do is actually just take the whole space. So right, so the whole X is also median. So how do you get the right metric? Well, it should be something that's a bit like an L1 metric. So you just take the L1 metric on every cube and take the induced path metric, and that works, which is the same thing you would do to define the Casio metric, right? Is also median with the path metric induced by the L1 metric on each cube, right? So each cube sits inside Rn, and you can just restrict the L1 metric there. Okay. So any questions so far? So so this is called like the Helly property. So in general, whenever you have a Casio cube complex, or the spaces that I'll talk about, if you have things that are convex and they pairwise intersect, then they also all intersect. So if you have finitely many things, they pairwise intersect, then the intersection of all of them is non-empty. So Nir wrote it for hyperplanes at the very end. It was an exercise, but it's also true for half spaces. It's true for any kind of things. And I guess we'll see more of this afternoon also. But yeah, so it exists. Other questions? All right. So, and again, you see, Casio cube complex is a bit like Rn that has disappeared. They have an L2 metric, the K0 metric, but they also have this L1 metric, and they will have an L infinity metric. Okay, so all these spaces, they're all good, they're nice, but they are, you don't really gain much from realizing that they're all median spaces. The median is an important part of the theory, right? In R trees, you want to have middles of tripods, and in cube complexes, taking medians helps. But this is not somehow the point of median spaces. So let me sort of give you the examples that are more relevant. So first, let me just quickly brush on this. So I'll say more about this tomorrow, but sort of median spaces arise from spaces with measured walls. So what does this mean? So if you have seen a bit about cube complexes, if you haven't seen anything about cube complexes, just stop listening for a moment. But if you have seen a bit about cube complexes, like the way you usually construct cube complexes is as sort of dual object to some family of codimension 1 subspaces of some set. But this works if your family of codimension 1 subspaces is countable and kind of discrete, doesn't accumulate around, and any 2 points are separated by finitely many. There are situations in which, however, you might have some uncountable family of codimension 1 subset, like some kind of foliation or family of foliations, and you still want to construct some codimension, some dual object. And if you are lucky, there is some kind of measure dual to this family of codimension 1 things, and that's what's called a space with measured walls. And the correct dual, the correct analog of a cube complex in that setting is a median space, which is just like a non-discrete version of a cube complex, essentially. Okay, but let me get to the 2 examples that I actually care about the most. And please don't be scared, because some people, understandably, just don't like the axiom of choice. But I do. I really like the axiom of choice, actually. Yes.
Is the R tree dual to a measured foliation on a surface a concrete instance point B?
Yes. And you can do something more. You can take 2 measured foliations, like the stable and unstable one of a Sudanosov, and you can get, essentially, you get the singular flat metric corresponding to that, but the L1 version of it. And then you get a median space that is very different from a cube complex, because all its hyperplanes will have a trivial stabilizer. And yeah, that's exactly it. Yeah. Okay, example E. So fix a non-principal ultrafilter. So if you don't know what it is, forget about it, right? The thing, they exist, right? Existence of these things is equivalent to the axiom of choice, which I take for granted. So let's go to omega. So this is just some object that allows you to take limits of things without worrying about whether or not they exist. It's something that ensures that you don't have to worry about subsequences converging to different things. It picks a limit for every, it picks a converging subsequence for everything that wouldn't normally have a limit. Okay, so this allows you to take limits of spaces in a very natural and easy way. So let's fix this. Actually, let's just fix it outside of the example. And here's the example. So say that xn is a sequence of K0 cube complexes. And say that you have been rescaling them a little, or that maybe you're not forced to look, to consider them with edges of unit length. Maybe some edges are shorter, some edges are longer, some stuff is getting contracted. So not necessarily with unit edge lengths.
But the edge length is constant.
No. It doesn't even have to be constant.
But in each xn.
Huh? No, it doesn't have to be. Like, edges dual to a given hyperplane should all have the same length. But yeah, but hyperplanes can have different thicknesses. We don't care.
Yeah.
Sorry? Cuboids, yeah, But the most important case of this is the case when in each xn, all edges have the same length, but this length is getting smaller with n, and it's getting shrunk. So these spaces are all discrete, but they're less and less discrete as n goes to infinity, and there is more and more geometry happening in smaller and smaller sets. Well, now we go to our lovely ultrafilter, and it gives us a limit modulo picking some base points, but I'm not gonna get into this. So there is, you can look at the ultra limit. This is a metric space, right? This is something you can do for any sequence of metric spaces with base points. And if you haven't been rescaling the cube complexes, this is still going to be an honest cube complex. But maybe you have been rescaling your cube complexes, so to like looking at them from further and further away, which is a thing that people do sometimes. And then all this is it. I mean, this is going to stay median, but that's all you can say, right? So lim is a median space. Yeah, absolutely, yes. So in particular, if you've heard these words, so in particular, or let's say, e.g., asymptotic cones of cube complexes are median spaces. No, I mean, ultrafilters are going to come up, but they're going to be a completely different concept that just happens to be called also ultrafilter. You absolutely, it's okay. This is just motivation. Like I'm telling you why you should care about median spaces, but you won't need to know about this ever again in the mini course. I mean, you will need to know about them, for example, F, but after that, it's going to be over. But also, yes. If I can say, like, this is really true. Like, it's really not that much work to learn about this stuff, and it's really useful. Like, you will not regret it.
Give us a crash course on those.
Yes.
To what extent that would be in, do you recover all median spaces in D and D?
In D, yes. In E, I think also. I don't think anybody wrote it up, but yes, yes. I mean, you might. The point is that I like to have ultrafilters on N. I guess like you might need an ultrafilter on some larger set if you really want to recover. I mean, yeah, the moral answer is yes. Then let's not worry too much about the details. You can approximate median spaces by. Yeah. From D? Yes, I'll tell you about it tomorrow. Where is Abdul? Ah, hi, yeah. Of course, yes. Yeah. Oh yeah, we'll get to it tomorrow and today also, actually. Okay. I mean, these are really, dual objects to family of codimension 1 subsets, just not discrete, just many. Why the hell would why would someone want to study asymptotic cones of cube complexes? The point is that usually people are interested in quasi-isometries, right? And quasi-isometries have that nasty problem of not being continuous because of that additive constant. But if you do an asymptotic cone, so you rescale your space and take a limit, like quasi-isometries become homeomorphisms, which is great because now you can use topology to abstract quasi-isometries. And if you want to study quasi-flats, then they become topological flats in the asymptotic cone. So if you're interested in quasi-isometries and quasi-flats, you should be interested in asymptotic cones because you can reduce very hard problems like studying quasi-isometries and quasi-flats to much easier topological problems at the cost of having to study them in much more complicated spaces. But that's the trade-off. Okay, and F, again, if you know about asymptotic cones, right, you know that R trees arise as asymptotic cones, but not just as limits of trees, right? R trees also arise as, asymptotic cones of hyperbolic spaces, which are not trees. They just kind of look like trees in a very weak sense. And the same kind of stuff is also true here. So let's say many interesting groups and spaces just coarsely resemble a cube complex in a very weak sense. And in particular, I'm thinking of hierarchically hyperbolic spaces, such as the mapping class group, which actually the mapping class group resembles a cube complex in quite a strong sense, right? It's quasi-symmetric by a result of Harry Pettit, but other hierarchically hyperbolic spaces maybe don't so much, I don't know. Also, you can look at more general things called coarse median spaces that will only resemble this in a very weak sense. And for any such space, if if you take the asymptotic cone, it is also going to be median. So, right? So more precisely, so if X is a coarse median space, so the precise definition is due to Bowditch, and I will not say anything about this in the rest of the mini course, but it's a general class of spaces. So for them, every asymptotic cone, it's not quite a median space, but it will have a canonical median metric, right? You will have to do some sort of small change, but it's all canonical. So every asymptotic cone admits a canonical median metric by Lipschitz equivalent to the original one that you would get on the AC. So again, if you were interested in sort of in quasi-flats and quasi-isometries of these spaces, this should be useful. Yeah, I don't think that's true, but don't have a counterexample.
Things being, so if you tell us names of stuff, you have to say what they mean when we're really, really, really curious. Please, we'll ask one thing that you named wrong.
So okay, if people still want to know in lecture 4, I will have time because I've kept things and I'll tell you what coarse median means because it's going to fit there, but not until then. Okay. Is this it? Oh, yeah. And so all the things I've said, like quasi-isometries and quasi-flats, they're only about topological property of the asymptotic cone. But if you're interested in studying automorphisms of these groups, if you're interested in studying automorphisms of cubulated groups or this kind of stuff, then naturally you will actually get some isometric actions on median spaces. And so then you will be interested in understanding actions on median spaces, although they will usually be very non-discrete actions, not proper. How am I doing on time? How long do I still have? Okay, that's good. Very good. Okay, so these are all the examples. So I hope I've convinced you that we should study these things. So the point is that when you want to study median spaces, you soon realize that the important stuff is not the metric. So the fact that they're metric spaces is just smoke there to confuse you. And the actual important part of the geometry is actually not geometric at all. It's combinatorial, and it's encoded just in this operator. And so it turns out that a surprising amount of the theory just can be carried out in a much more abstract setting, and it is actually quite useful and easy to do that. So I will now abstract for a moment and forget for a second about median spaces. Let me tell you what a median algebra is. And I'm going to put it here so that we keep it. Okay, so a median algebra is a set a priori with no additional structure, except that it has a ternary operator with a map M that's equals triples of points of M and spits out another point that satisfies some identities. Okay. So first identity. Okay. So what are we doing here? We're modeling what that map there does. Okay. So first thing, M is symmetric. So if you permute the 3 point, the value will not change. Okay. Second. Well, if you find every point happen to be equal. If it's meant to mimic what's going on there. If X, Y, and X, they are equal, really has to be that very same point. So this should hold for any X, for any Y. Okay, now let's get to something that's a variant, but bear with me for a second. This you can do it's possible point condition, you can do it in kind of some kind of activity. So let me write it. Talk about it. Okay. This holds for any 4 point It's also called the associative rule. Right? How do you see the associativity? We have 4 points, but now one equal B is singled out because it appears right? And if we view taking median with B as some kind of binary operator, we're saying here is that that binary operator. So it's not immediately clear that this satisfies this, but it's also not that hard to see. It's going to be in the exercise, and you'll see it on Wednesday again. Let me add a fourth identity. So this fourth identity actually follows from the first 3, but this is hard. Okay, so let me include it in the definition because that's what's easier to use in practice. This is called the 5-point condition. Not very imaginative. Can everybody read that? Or... Sorry. No. I'm not gonna fall for that. Yeah. No. I mean, I have no geometric intuition for what this means at all. So let me tell you something about it, though. Sure. Let me tell you how I think about these things. So this is a very algebraic theory at this point, but so by the end of today, I'm gonna have told you that you have half spaces, and the moment you know that median algebras have half spaces, you don't need to use those identities ever again somehow. And that, as far as I'm concerned, the theory is just using half spaces. But up to that point, this stuff is important. And actually, let me sort of give you some history here. So facts. So clearly M3 in M3 prime, so the 5-point condition implies the 4-point condition. So this is obvious. Just take B equals D. I think that should work. Okay. So what is a much less trivial result is that M1 plus M2 plus the 4-point condition implies the 5-point condition. Right? So this is hard, but it's really harder than you might expect, just because there isn't much that you can do, right, from starting from this. So we might expect that it's just like some application of identities, but it's really pages and pages and pages. So so this is like the real hard work was done by Schalander in 54, who proved a stronger result. It's not quite this, but this is really where the juice is. Then in the 70s, Colibiar and Markizova. I would not recommend it as an exercise. It's not fun, and it's also like, I mean, it's really hard. Like I'm not, yeah. So yeah, so they observed this, and essentially Shalander's result implies this, can be used to gain this. And then there is a proof by Donald Knuth that is more recent, and this is simpler, but it's still hard. So you see, a lot of people are interested in like median algebras, because this is really a very, somehow it's the most basic or most fundamental ternary thing you can do. And people who are interested like in this from order theory, like interested in like distributive lattices or things of that sort. And then they're also relevant in theoretical computer science. So I don't exactly know why. But so the point is that M3 is quite easy to check. So if you want to show that a median space is a median algebra, M3 is the thing to check, and it's not hard. Then you use this black box, you get the 5-point condition, and then the 5-point condition is actually quite powerful to prove all sorts of things, and get to the existence of half spaces. And once we'll have half spaces, the theory changes flavor quite a bit, or at least that's my perspective on it. I of course accept to be corrected. So yeah, let's put it here. Theorem/exercise. So if X is a median space with median operator M, then XM is a median algebra. No. It's going to be in the exercise, and you'll check M3. This is easy. Show it. Yeah. Yeah, I think so. Like if somebody has a direct proof of M3 prime for median spaces that doesn't go through this, which could exist, I'd be happy to see it. But I was thinking about it when I was preparing the mini course and I couldn't find it. Although I admit I haven't thought about it that long. So maybe there is. Yeah, that's maybe an exercise plus. Also, like, yeah, I'm not very good at using these identities because I never use them. Okay. Okay. Yes. Sorry? No. So every countable median algebra is. If you go bigger, it's not true. And if I were doing better with time, I would tell you that you're going to see one in a moment, but I can't promise you that. Okay. Okay, let me give you some definitions. So I'll define what I need to define half spaces. And all that I define now is going to get used a lot throughout the rest of the mini course. So first of all, intervals, right? So definition one is intervals. So if x and y are points in M, from now on, for a while, I will just work with median algebras, not median spaces. So if you have 2 points, the interval between them is the set of points such that if you apply the median with x and y, they don't change. So why do we define it this way? So what you should realize quite quickly is that if we are, like, if our median algebra happens to come from a median space, then this is the same as saying points on a geodesic between x and y. Okay, so points that are efficient, like they don't make you lose time if you go through them. And if the space is geodesic, this is the same as saying the union of all geodesics between x and y. Okay, but we're just in a median algebra. We don't have this geometric interpretation a priori. So this is the interval. Other definition. So here are some important subsets of a median algebra. So first of all, we want to define subalgebras, right? Well, predictably, these are just subsets. Let me call them S, that are closed under taking medians, right? So I'm going to write it this way. You take the median of points of S, you stay in S. Okay. So then there is a notion of convex set. So, and okay, so I'll define it this way. So it's a subset C, such that it's closed under taking medians, but one of the 3 points might actually not be in C. It might be an arbitrary point of the median algebra. Okay. So again, so to sort of see why this is called convex, think of what happens when your median algebra happens to come from a median space. And you will realize that this is the same as saying, in fact, this is true in any median algebra. Let's not do it in green, right? So what you can check easily is that this is the same as saying that C is closed under taking intervals. So if you are in a median space, all we're saying is any geodesic between points of C stays in C the whole time. Okay, and finally, let's go here. Half spaces. So a half space is a subset such that, well, it's convex and has convex complement and non-empty. So such that both H and its complement, H star, are convex and non-empty. Okay, this is a definition. How long do we have? Something like 10 minutes? Less? 5? 12? Oh, great. Okay, so here's the important point. This I will actually prove tomorrow because this is really what gets the whole theory started. So here's the theorem. So in any median algebra, half spaces exist, And actually, a lot of half spaces exist. Like you can really separate any 2 points by them, or in fact, any 2 disjoint convex sets. Right. So distinct of any median algebra. Right. So let's say here, M median algebra. Distinct points of M are separated by a half space. So what do I mean by this? Because maybe this is not how you think of separation, right? So if X is different from Y, there exists a half space H such that X lies in H and Y lies in H star. Okay, and you see, so this is how like the important theorem. You see, the complement of a half space is again a half space. And whenever you have a half space, it's going to give you a partition into 2 convex and disjoint things, and both of them are half spaces. So this is exactly what is happening in a Kazhdan cube complex when you have a hyperplane and you look at the 2 connected components of the complement of the hyperplane. Some people like to also define a wall in a median algebra as just the partition is the wall, right? You artificially define this partition to be a wall, or like the pair of half spaces to be a wall. I'm not going to do that, okay? So because like somehow walls in median algebras are just a hallucination, right? They're a hallucination, yeah, when you've like been doing too many cube complexes. But it's a hallucination that I'm also prone to, right? But like they don't really exist here. Okay, you don't have a codimension 1 subset in the median algebra. You will have such subsets in good median spaces, but not in general in this abstract setting. Okay, so I'll prove this tomorrow. Okay, then let me conclude with one example. And this is just to make Macarena happy. Because I haven't really given you any examples of median algebras that are not coming from median spaces, but they are quite a bit more general. So let's see sort of like what universal median algebras look like. So these are called Boolean median algebras. Oh, are there any questions before I get into this? Okay, so this is the construction. Say that omega is a set, any set. Well, you can look at, well, its power set, right? Just the collection of all subsets of omega. And this has a natural median operator, which is the usual majority vote kind of stuff, right? So you look at every point of omega, and you need to decide whether it lies in the median or not. So you ask A, B, and C, see what they tell you, and you just do a majority vote on that, right? So these are points of omega lying in at least 2 of the 3 sets. You can check that this map satisfies that. This is really not hard. So this is a median algebra. So let me tell you why this is universal. So this comes from that theorem about half spaces, right? So every median algebra can be every median algebra is a subalgebra of a Boolean one. So you start with M. You look at the collection of all half spaces. Okay. And now, well, we do what we did to define the median in a cube complex, right? So M can now be embedded in the power set of the set of half spaces just by sending every point of Mx to the set of half spaces that contain it. Okay, so this is injective because of that theorem, right? If you have distinct points, there is going to be a half space where they disagree. And this is actually a median morphism, right? So if you want to know whether the median lies in a half space or not, It's just whether or not that half space contains at least 2 of the 3 points. And you can really check this just using convexity, right? And this just from the definitions. All right, I think I should stop here. Yeah, thanks for listening.
Yeah. So the thing is like very big cube.
Is it a big cube? Kind of, yeah. But it's, so to answer your question, when omega is big, when omega is R, something like that, having a metric here that is compatible with the median operator would be a bit like having a measure that's defined on all sets. And we know that's, yeah, not possible.
So like to give an example, you can take a very large ordinal, and take an order set, and the median is just the uniform. Ordinal is large enough.
Yeah, so I was wondering about this because like somehow this is cheating because this is bigger than the cardinality of the continuum. So I don't know if any median algebra that has the cardinality of the continuum actually comes from a median space. I would guess probably not, but I don't know. These are kind of artificial questions, though. I mean, like, yeah, it's not. Yeah.